Hi guys, in this video I'm going to demonstrate how to build a linear regression model using R programming. So linear regression is the technique which is finding the relationship between the variables. So it means finding the relationship between the target variable and other predictors. So here the terminology is no, you can say y is a dependent variable which depends on x. In other terms, we say this x is predictor. There can be multiple predictors. So regression is the technique to find the relationship between the variables of the data sets. And there are two types of regression. One is simple, other one is multiple. So simple linear regression means finding the relation between only two variables. So one target variable, here y, which we call it as dependent variable, and x is called as independent variable or predictor. Then what about this a and b? So b is the intercept, and uh, a is the no, coefficient of x. So when you fit this data to the when you plot the graph, so you can see what is the intercept value and what is the coefficient value, and also you can see the value for x. So when you supply x and then a and b are automatically calculated, then you'll be getting the value for y. So the core idea over here is to find the best fit line so that the data is fitted. So the model which fits all the data is called as best model, and you can evaluate that by using the measures like R square. So in multiple linear regression, you will be having multiple independent variables. So the difference over here is in simple linear regression, we just have two variables, whereas in multiple linear regression, multiple variables are there. That means you can have target variable, along with the target variable you can have set of independent variables. So we'll take an example for this, how to build a linear regression model in R. Before that, I just want to show you a simple example where you would like to find the relationship between the height and weight. So I just took the sample data. So these are the height values, and here we have weight values. So this is a vector. These two are the vectors. You can see them here. So it's a vector, and then I'm just plotting a graph to find the relationship between these two. So when you plot a graph between the weight and height, you can see, so weight increases, then height also increases. Or you can plot this in reverse also. Weight is dependent on height or not. And then you can have a little bit enhanced graph like weight and height. We are specifying these values, parameters like PCH, so which gives the solid dots instead of having these white dots, white empty dots. And we are taking the variable CX. The value is 1.3, which gives the bigger dots than the normal one. And this is the title of the figure: height versus body mass or weight. And then this, on x-axis we are showing the weight, and y-axis you are showing the height. So you can find the relationship over here. We just write this as a weight. So x-axis label, y-axis label, and then you can see the relationship. So you see here you have weight, and here you have height in centimeters, and you have a very good plot, no dots. So if you plot a line, that line must fit these points, then only the particular model is best. Understand? So in order to have a linear or a linear regression model, we can use the function LM. LM stands for linear model. So the equation is this: height is depending on weight, and then printing the relationship here. So relation is a user defined variable, and you can see the formula here. And the intercept value, that means intercept is 98.0054 and weight is 0.9528. So we have got the value for intercept. B, in other terms we can also say this is beta 0 and this is beta 1. So the equation over here is the height, right? The height is equals to beta 0, which is 98.0054, plus beta 1, which is 0.9528, multiplied by the weight value. So if you supply weight value, then you can know the value for height. And then having a summary of this model. In the summary you can see intercept and no, coefficient values, and then you weight values here, and you need to observe this last column, which is a p value, probability value, and we expect this value to be closer to 1. If it is 0, if it is nearby 0, then poor fitting. And this model can also be evaluated by r squared. So multiple r squared value is 0.81226, and adjusted r squared value is 0.7891. As you know, that there should not be the difference between these two values. So if there is a high difference between these two values, then that model is not considered as a good model. So if you add the number of variables, then the model is penalized. So that's why the difference between this multiple r square and adjusted r square value should be less. So this is model evaluation, and you can also plot this. We can also have a line by specifying the beta 0 and beta 1 value. So AB line of 98.004, which is intercept, and this is beta 1, and you can add a line by specifying these two. So you can see this is the line which is plotted. And then you can also have the same thing can be had like this, height equals to weight. That means we are specifying the equation. By using this also you'll be getting the same graph. So this is the simple example where we are taking two variables, weight and height, and finding the relationship between the two variables. So here the relation is positive to positive. That means if one value increases, then the another value increases, right? So here weight increased, then height also increased, right? So this is simple example. And next, importantly, I want to take this data set as an example for linear regression. So MTCAS is a data set which is coming with RStudio, and this is a motor trend data extracted in the year of 1974. And this data set consists of 10 variables. That means 10 aspects of automobile design and performance for 32 automobiles. So 32 different automobiles are there, and 10 variables are these: MPG, which stands for miles per gallon, C cylinder, displacement, horsepower, drag, weight, is quarter per second. VS means engine type. So there are two types of engines, zero shaped and one means straight. And this transmission, so means 0 means automatic transmission, 1 means manual transmission, gear means the number of forward gears, and carb means number of carburetors. So these are the 10 variables, and we would like to find the relationship between the variables. The analysis over here is an automatic or manual transmission better for mileage? MPG. MPG means mileage. And we need to also quantify the MPG difference between the automatic and manual transmission. So these are the findings over here. So let us analyze the data. Even if you search for if you don't know what is this data, you can just search out here in MTCAS. Just type and press enter. You can see the help. So this is the help, motor trend car road test, and you have the description on the data set. So I copied this in my presentation. There are 32 observation, means 32 rows, and 11 variables are there. And 11 variables are there. And then we'll be having the example for this also. So I'll just clean my screen, user interface. So just here I'm loading the data set, right? I'm loading the data set. Data of empty cars is a data set which is coming with the RStudio also. So data of empty cars, then the data is loaded, and then head of empty cars means we are displaying the first 6 rows of the data. So this is the data set. Even if you click on this, you can visually see the data sets. So these are the variables, MPZ, cylinders, and you have 32 cars data. So this is the data frame, and then um, we are finding, so filtering the data. So transmission automatic. So these are the user defined variables. Transmission automatic equals to empty cars of MPZ, where AM0, here AM0 means automatic. So 0 means automatic, 1 means manual. So we are just filtering the getting the MPG values for which um, automatic transmission. So just getting the summary also. So you can see these are the values, and if you take the summary descriptive statistics, minimum MPG value is 10.40 and maximum value is 24.40. The average MPG is 17.15. Next, I'm also getting the manual transmission MPG values. So TR manual, empty cost of MPG for which AM equals to 1. So getting the manual transmission. So you can see the minimum MPG value is 15.0 and maximum is 33.90. If you just look at the results, right? So with our eyes we can see maximum MPG value in automatic is 24.40, whereas in manual is 33.90. So but just by looking at that data set, we can say manual transmission is better. Understand, manual transmission is better. So we are just plotting the relationship between these variables like MPT, MPZ, and weight and color equals to blue. So what is the dependency on this? So if MPZ increases, then weight is decreasing, like that. So I'm just taking this weight variable, right? And then this is simple linear regression. So just taking two variables as I've explained. The equation is MPG depending on weight, then having the summary. So you can see the intercept is 37.2851 and beta's coefficient is minus 5.3445, and the dependency, you can see the significance code of weight, 3 stars. The meaning of 3 star over here is this 0 is near to 0. The probability value is nearer to 0, so not poor fitting, right, which indicates poor fitting. And then we are building multiple linear regression model. So how the MPG, right, how the MPG is depending. Before that, you see, just include, if you include all the variables, MPG tilde operator dot means all the variables. Now after this you can see the results. For this you can see the results. Look at the last column. So which value is higher? So that means this cylinder is 0.91, so more fitted. And next is this one, VS engine type. Next is AM transmission type, right? And this one gear and carburetor. So the top four are cylinder, next VS, next carb, right? So like this. So you can build a model with the important variables, and you can see the difference between the when you are fitting all the variables. The difference between multiple R square and adjusted R square is almost 0.06%. So p value is closer to 0. This e to the power minus 0.07, so closer to 0. So poor fitting. So it depends on the data, so we cannot change the data, right? Now I'm building a model with these four, right? These four: cylinder, carburetor, VS, and AM. And data used empty cars, then taking the summary. So if you take this, So this is the result, and you see multiple R square and adjusted R square values are 0.81, here is 0.78, so 3% difference, right? Now just supplying these values, right? So I'm just using my model. So first of all, creating a data frame. So test1 is equals to data dot frame, cylinder value giving as 4, carburetor is 2, vs is 1, am is 1. Then I'm using my model. This is my model name, and test data is used, then it will make the prediction. I'm also printing the value for prediction. You see this is the predicted value 27.4321. so this is the MPG predicted. This is using the manual transmission. So if you use if you use the AM0, right? 0 means automatic, right? So AM0, the same values, then what the model will make the prediction. Let's compare, right? So automatic is giving less MPG value, 22.87. So we concluded that manual transmission is better. Understand, manual transmission is better. So even we have seen with the observed data, means actual data, so manual transmission is better for good mileage. So we have answered this question. So which transmission is better? So the our manual transmission is better, and we have quantified the difference between the automatic and manual transmission, and we have also quantified the variables by looking at the summary. So which variables are more fitted? So by looking at this last column, PR, probability value, so more value means more fitting, less value means not fitted. So the model is evaluated by R square, right? So if you plot a line like this, so if there is a difference between the line and the point more, then that is called as error. So the one of the evaluation is a good way to test the quality of the model is to look at the residuals. That means residual means difference between actual value and what the model has predicted. So if there is a difference, then we can say this residuals. You see this is a straight line, and the values are not falling on the line. So if the values are falling on the line means they are fitted, and if the values are not falling on the line means they are not fitted. So a model is expected to fit all the data so that the residuals are less. Understand, the residuals are less. So you can see the residual summary here. Residual standard error is 2.65, and with the previous one you can also see the residual error 3.04. so more it is more, right? So the number of residual values should be no less. You need to check this residuals, minimum residual and maximum residual. You can also see average residual value, so the error should be less. So this is about linear regression. Do follow our videos to have the future videos on the R programming and machine learning. So thanks for watching. See you next time.